Welcome everyone to episode 43 of Games with Go, where we will begin OpenGL, coordinate systems, and matrices. This is where we make the 3D, really 3D for real, and start working towards where we can have a camera or point of view that we can rotate or move around through a 3D world. So to get started, we want to have an actual three-dimensional thing to play with. So far we've just had a triangle or two triangles combined to make a quad. So let's make a cube, and so that you don't have to sit here and watch me type a bunch of floating point numbers, I've made a gist of the floating point vertices for a cube. I'm going to paste that into chat. And you can grab that and just copy and paste it into your code and save everyone a bunch of time. So we'll take our old vertices for the quad and just replace it. So this just represents the 6 faces of a cube. And we're not going to be doing the element and buffer array trick for this one, so we can get rid of the indices array, and all of this element buffer array setup stuff can go away. And the second vertex attrib pointer was for setting up the element buffer array as well, so we can delete that as well. And I think the rest of this stays the same. We still have 3 floating point values and a UV coordinate. So all of this should still be valid. Oh no, that's not true. We have a, yeah, we still need both vertex attrib pointers because the second one is for the UV coordinates. So we have the 3 x, y, z positions for each face, and then the UV coordinates, which is what the second attrib pointer is for. All right, then we'll scroll down to where we draw it. We're not drawing elements anymore. We're going to draw arrays, and it's still triangles. Let's see. I think here we're going from, what is it? Let me see. $36. Okay, so if we save this and run it, go into hello triangle. Okay, it still pretty much looks like we're drawing a quad, and that's just because we're seeing our cube kind of head on. And we haven't actually done any of the sort of 3D coordinate system stuff we need to do to be able to look at it from any other point of view. And that's also why it's not square. It's kind of matching the shape of our window. All right, but we've got a cube set up in memory here. So that's where we're going to start. So the next step is, how do we set up a system where we can render this cube from different orientations, like move the cube around in the world, rotate it, move the camera around, and have it look correct? And the answer is we use a lot of matrix transformations. So let's open up the drawing program. Okay, so what we've done so far is just make things in what we call local space. So local space. So if we make a cube in local space. Then we sort of define the center of the cube as coordinate 0, 0, 0. And everything is in terms of sort of whatever value you want. If you wanted a cube that was 1, where each side was length 1, then the coordinates would look like something like the z coordinate would be from -1 or minus 0.5 to 0.5 and so on. And the x coordinates would go from minus 0.5 to 0.5 and so on. So your cube would just be set up in terms of local space with 0 at the center, and then where are your vertices in relation to that. But at some point we want to render a whole world, right, or a whole level, or zone, whatever you want to think of it. So we need to transform local space into world space. So the world might have multiple cubes, right? You might have one cube up top. You might have another cube over here, and it might be rotated. There's no chance I can draw. Well, sort of. It might be rotated in a different way and located at a different position. So to get from local space to world space, we use a matrix. And in order to do that, you need some extra information. You need to know where each cube is located in space. So each cube here will have to have a position and then some data indicating how it's rotated, right? A rotation. And so if you've got this information, you've got the local space coordinates and then a position in the world and then some orientation or rotation, you build a model matrix. And the model matrix lets you multiply your cube by the model matrix to get into world space. And a matrix, you just think of as a two-dimensional array of numbers, right, of a certain size, certain dimension. Okay, so you set up your model matrix for each kind of distinct thing in the world, and you multiply the local space coordinates times the model matrix, and you get world space. All right, any questions so far? So the stuff can be pretty challenging. What you aim to do eventually as you sort of build your code is you abstract all of this away. So what we're going to do eventually is get it to where we have like a camera class and we have objects. And we don't have to do all this stuff by hand all the time. Once you set it up, you can just put things at locations and your code will make all of this happen. But someone's got to do it the first time, and it's a little bit tricky. So world space is a good start, but we don't have true 3D monitors, so we can't actually render a world space. So we have to turn this 3D view into some kind of two-dimensional view. So the next step is you need to get into view space. And to get into view space, you use a view matrix. And the goal of view space is to take your three-dimensional world and project it into a two-dimensional world. So to do that, you need some point of view or camera located at some particular space, and it needs to be pointed in a certain direction, right? So you can think of this as your camera. What would it see if it was located here, looking in that direction? Right, so what it might see now becomes two-dimensional, right? So it might see a couple of squares. Maybe they overlap a little bit from its point of view. Okay, this is where things become 2D. And we get from here to here by using the view matrix. And then the next step is clip space. And clip space is similar, except that we kind of condense everything from coordinates that range from -1 to 1, and anything that falls outside of -1 to 1 is removed, right? So the camera might be able to see all kinds of stuff out in the distance, but only so much is going to fit on our screen eventually. So we want to get rid of the stuff that doesn't fit or that's too far away. So clip space, we might imagine we don't see all of that second square because maybe it's off the screen, for instance. And then finally, you get to screen space, which will go from 0 to the width or height of your resolution or your window. All right. That's a lot of stuff. So we'll take it one step at a time. Any questions so far? So we're going to need to set things up so we can make our cube have a position and an orientation, and learn how to build a model matrix so we can get to world space and then view space and so on. So first change we're going to do is to our Vertex Shader. Our Vertex Shader is going to need to know about these matrices in order to do the transformation. So along with the data we're taking in so far, the position and text coordinates, we're going to take in 4 matrices. Model, view, and projection. And by the way, I'm getting the syntax highlighting on shaders with an extension. What's it called? VS Code -shader. If you just search for shader, this should come up. And if you install it, it'll recognize, give you syntax highlighting, which is nice. Okay, and so when we have our matrices, the position, our vertex positions get transformed by them. So we don't use just the raw X, Y, and Z anymore. We multiply our matrices together. So our raw local space gets multiplied by the model, by the view, and the projection. All right. And let's see. We're going to change our text coordinate a little bit. Okay, that sets up our Vertex Shader. All right, now we're going to want some positions for our cubes. So we'll make more than one cube. We'll so we're going to use our MathGL library here. So I think we set this up last time. So typically when people do OpenGL and C++, they use a library called GLM. It just has a lot of matrix and vector math functions whose results come out in a form that OpenGL is used to working with, so you don't have to do any adjustments. And for Golang, there is a pure Go equivalent library called MathGL, which is what we're going to use. If you haven't set this up already, you should go watch the previous video and get it set up. Okay, so we're going to use that. We need to import it. We're using MGL32 because we're working with 32-bit floats. So cube positions. OpenGL 32 vec3. So we're going to have a slice of vec3s. So we'll do let's just do 2 cubes to start with. We'll go up from there. So we'll do one located at the very center. How do we get new vec3? I think actually vec3, let's go look, is just in a slice. So I don't know if we even need to use it. Let's see. Okay, we can build them this way with the struct syntax. Okay, let's try that. All right, there we go. And all right, that'll be it. We'll just have 2 cubes to start. Now we need to set up our matrices. So we're setting up our shader. Oh, this was for our old star fields. We're not going to set these floating point uniforms anymore because we're not using our star field right now. Okay, so we need a, let's start with the projection. So we're going to do a projection matrix. And there is a built-in function called perspective that can build one for you. So you're giving it a field of view, which is how wide of an angle your camera can see. And so we're going to start with, we'll start with 45 degrees. And there's a built-in degree to radian converter, because we're actually going to pass in radians. And if you don't have radians memorized, you can just convert it. Aspect ratio is the aspect ratio of your screen. So we're going to take the, we're using for our width and height. Win width and win height. So that'll be the float win width divided by the float 32 of the win height. That's our aspect ratio. And then near will be the nearest something can be and we still see it. Because at some point, if something were to touch the camera or to be too close to the camera, we just skip it. So that is the nearest something can be and still show up. And then far will be how far away something can be before we stop trying to show it. Sometimes the hard part is spelling. Okay, that sets up a projection matrix for us, thanks to MathGL, so that's not too bad. And the view matrix we'll start with NGL 32. Let's see, we're going to want a map 4. I think we want the identity matrix. Let's see how we get that. Okay, we can do ident 4 probably. There we go. Yes, okay. So that gives us an identity matrix, which, if you're not familiar with math or have forgotten, you can look it up on Wikipedia. It's basically where everything is zeros except along the diagonal you have ones. So if you get to linear algebra in school, pay attention if you want to do 3D, because it's constant. And I didn't, and it's hard. All right, so we have an identity matrix, and then let's see what we want to do with it. All right, so we're just going to pick sort of a camera position of sorts. And then we're going to set these. We need to set these matrices in our shader. Set the uniforms. That are in our Vertex Shader. So let's go to shader.go. So we have a function to set floats. We need to make one to set matrices. Call it set map4. This is the 4x4 matrix. And we'll need to include MGL32 in here as well. That's an MGL32 mat4. All right, so their name and location, just like we always do. And now we're going to call GL uniform matrix for FV. 4x4 matrix, floating point. We got the location. The count is going to be 1. I think the transpose is false. Always. And then the value. So the mat4 type is just a array of 16. So we can say, because 4 times 4 is 16, so it's just 16 floats. So we can just cast. And then it wants a pointer to the first value. So I think we can just do that. So we're casting it to a float array and then giving it a pointer to the beginning of it. I think that will work. Maybe not. Okay, so now we have a setMat4 utility function. Let's use it. Hello triangle.go. So we're going to say shader program setMat4 projection and view. All right, but we also need the model matrix. Now remember, we have 2 cubes. We have our array of cube positions. So we need to make a model matrix for each one of these, right? That's where we take our local space cube with a position and rotation and convert it into world space with a model matrix. So again, we're going to want an identity matrix to start. And the first thing we're going to do is translate the model in space. That just moves it up, down, left, right, in or out. So for that, call model.translate. What does it expect? Do we just multiply? Okay, transform coordinate is what we want. Yeah, so that will be the vec3 we're getting from our cube positions. Let's call this position because that's what it is. And the identity model matrix. Oh, transform is wrong. We want to translate. Okay, I think it's just the translation result times the old model matrix. These are functions. Why can't we multiply? Oh, that makes sense because Go doesn't have operator overloading. Okay, there we go. Mul. So we call it explicitly. This is a little bit different than GLM. So let's see. Translation. Is that all we needed the whole time? That's easy. The order here matters though, and I'm not sure that's right, but we'll see. Okay. Back to making some progress, hopefully. So this translated, but we also have to have some sort of rotation orientation. So we'll make each one angled a little differently. So we'll just give each one a different angle by multiplying by I. Now we're going to say MGL32 rotate. Let's hold off on the rotation for now, because I am unsure about how to use MathGL for that right now. So let's see if we get the translation working first. Fewer variables to worry about. Okay, so then shader program set mat for model. We're not going to need I for now, so we underscore that away. Let's see, the texture in vertex array only needs to be bound one time. We need to draw the arrays for each cube. We don't have this X anymore. I'm going to get rid of that. All right, let's see what we get. Syntax error in our vertex shader. Forgot semicolon there. Oh, capital C. All right. So now if you look closely, you might notice that these are kind of looking like cubes a little bit. And we see one and another. And it's smaller because it's further away on the z-axis. So we've got the translation working, it looks like. That is pretty cool. So something we can do real quick with this. Let's see what time it is. 8:42. Okay. So we can have a very simple kind of movement. So let's set up a keyboard state. So we're going to get our keyboard state. We'll do, let's see. we'll just do X and Z. Okay, so we're going to have X and Z starting at 0. Then when we build our view matrix, we're going to translate by X and Z. And then we'll say if keyboard state scan code left. We'll do X .1. This is going to let us move left and right and in and out, hopefully. Maybe too much at a time, we'll have to see. Let's give it a try. So we are moving back and forward. Left and right. Pretty cool. So we've made Quake now. So one thing you might notice is the cube looks a little funny as it moves. And that's because the way we've done things so far is it is rendering every face of the cube, even if it's a face that's behind another one. Right? We have to actually do some work to make it not render things that are covered up by closer things. You can kind of see that as it moves from one side to the other. All right. Any questions so far? Smashing SF says he thinks the homog rotate will be the rotation function we want, so we could give that a try. And yes, depth testing is not currently enabled, which is why we're sort of seeing all of the faces of the cube, even if they're behind another one. Okay, let's try the rotation. We know translation's working. So let's see, we've got NGL 32 dot turns a map 4. Excellent. Okay, then we can give it the angle we want. Okay, or the axis we want, not just X, Y, or Z. So we'll do our angle and do a NGL 32 vec3. Just give it a random off-center axis. And multiply our model matrix again. Bring back the I, because now we're going to use it. It's exploded. Let's see what's going on. Oh, we didn't do the radians conversion for one. There it is. So one thing I think is, I'm going to try something. Yeah. So we were doing the translation first. Yeah, the translation first and then the rotation, which meant that the rotation was happening, it wasn't rotating the cube about itself, but it was rotating the cube about the 0.0 point, which we had translated it away from. So that's why when we do the translate first and then rotate, our upper cube moved kind of off screen like that, because it wasn't just rotating in place, but about its old center axis. So if we move the rotation first, before it's been translated, then the cube just rotates about its center instead. So our old cube is where it used to be, just rotated a little bit. Okay, and the way we've set this up is we can make mini cubes. Right, we can easily add a third. For instance. There it is. And you can play around with, try and make, 100 cubes, 1,000 cubes, see when things start to break down and get slow. All right, what are we at? We're at 8:51. So I think that'll be it for today. Smashing SF says add a normalize at the end of vec3, otherwise it will get funky. Do you mean this vec3 here? I think this is normalized. I pulled this from an example. I guess it can't be normalized if one of them is already 1.0. But it might do that for us behind the scenes anyway. Anyway, that is it for tonight. What we'll be doing next is setting up a camera. We'll start setting up a camera so that we can rotate the camera, move the camera around, and then it'll do all this work for us, right? So instead of our interface being manually setting up all these matrices, we'll just say, let's make a camera at this position, rotate it this way, and then it'll show us the scene we want to see. And that'll let us do like a simple mouse look thing where we can move the mouse around to look a certain way and then use WASD to move through the scene. All right, so that'll be what's up next, setting up the camera as a utility function. It'll be part of our GoGL stuff with the shaders and everything. All right, any questions about tonight's stream, previous streams, or programming life in general? I'll stick around for a few minutes in case anyone has something. And I'll put a note in there about normalizing that. Smashing asks, any thoughts about how to gamify this, asteroids or Minecraft? I was actually thinking something like a 3D asteroids with a planet and stuff. We could combine our, we could use our simplex noise to make a cool procedural texture for a planet, and throw a bunch of asteroids in the world and maybe shoot them or something. But a lot of work to do before we get there. Such is life with 3D. All right. I think too, next time I'll use a different texture. This texture is cool, but it's really noisy and hard to see what in the world is going on. So we'll find a more calm texture for this. And you can see how, remember we have a minimum near value for the camera, so if we get close enough, we stop seeing it. It goes away. All right. Good night, everybody.